Hi thermophiles. So in the last video we learned how to calculate an adiabatic process. We learned how to calculate the different state functions associated with it and the heat and the work associated with it. And we can also do these calculations for isothermal processes, isobaric, and isochoric processes. And with the combination of these, we can construct a whole bunch of different engine cycles. The next one we're going to construct is the Carnot cycle. We did the Stirling cycle early in class. And from the Carnot cycle, we'll be able to calculate theoretical heat engine efficiency. What emerges from the cycle, we won't talk about that in this video, is the idea that heat engines not only need a heat source, but they also need a cold sink. And from Carnot's theory, we also can derive a thermodynamic concept of entropy, which is different than a molecular concept, and we'll do both. So we'll get a thermodynamic concept of entropy. And the Carnot cycle, from Carnot's theory, he was actually the first person to make a statement of the second law of thermodynamics. Interestingly, the second law, actually I'll say this later. Yeah, I'll come back to that later. Before we start the Carnot cycle, the history of the Carnot cycle and the state of thermodynamics at the time is fascinating, and it's a fascinating example of how science can proceed and sometimes how science can stall. So Carnot published his work. So I'm going to make some statements and I'm going to write down some things just to point you to resources that you could look up. So Carnot, in 1824, published Reflections on the Motive Power of Heat and on Machines Appropriate for the Developing this Power. I'm going to just write the first part of the title. At the time, the dominant theory was something called the caloric theory of heat. So people believed that there was an actual substance called caloric that flowed between objects to transfer heat between two objects. The caloric theory lived way longer than it should have. So the first experiment that should have killed the caloric theory was in 1798, Count Rumford did what's known as the cannon boring experiment. And in 1799, Sir Humphrey Davy did an experiment where he melted two ice cubes using friction. And these two experiments should have killed the caloric theory, but what happened instead is proponents of the caloric theory reinterpreted the analysis to basically further confirm, in their minds, caloric theory. When Carnot wrote Reflections on the Motive Power of Heat, there is some evidence that he was beginning to doubt the caloric theory. But he was inspired by, when he developed his cycle and when he wrote this paper, he was inspired by water mills. And he modeled the flow of caloric, or the fall of caloric, from a hot source to a cold source based on what he was observing in water mills. But we have evidence in letters to his brother that he had misgivings at the theory at the time, and what we don't know is whether he had abandoned for himself the caloric theory at the time, in which case he wrote Motive Power in terms of caloric theory for it to get broader acceptance, or maybe he was still wavering at the time. We don't really know. It wasn't until the mid-19th and the mid-19th century that other theories surpassed the caloric theory. So there's when caloric theory began to decline. But we have evidence of publications into the 19th century, the survival. It took until then for caloric theory. to die. What eventually killed caloric theory were experiments done by James Prescott Joule. So James Prescott Joule, what he did, quantified the relationship. He quantified the equivalence between mechanical work and heat. So he eventually did 4 experiments, all of which were different devices to show the mechanical equivalence of the quantitative equivalence of mechanical work and heat. He published his first in 1843 to the Royal Society and was met with complete silence, and none of his other work in regard to caloric and mechanical work were admitted by the Royal Society. The other 3 experiments came between 1843 and 1850. They're all 3 completely different ways. He devised devices that converted mechanical work and generated heat and made measurements, and they're all 3 completely different devices, so I think they're interesting experiments that can be looked up. There's lots more that can be said about these experiments and all of these names, which are probably familiar, and how they intersected with other famous names at the time to evolve what we currently know. I will say it's interesting, I find it interesting, the asynchrony of our laws of thermodynamics. So the temporally first law to be devised was the Second Law of Thermodynamics, which Carnot developed in 1824. It wasn't then until Joule in about 1850 who developed statements of the first law of thermodynamics. The zeroth law of thermodynamics didn't come until the 1900s, and the third law of thermodynamics didn't come until after that. I'm not sure how they eventually came to have the names that they do now. Okay, so for this video, all we're going to do is tell you what the Carnot cycle is, and we're going to make sure that we can calculate all of its steps. So there's a worksheet on the Canvas website under a list of assignments for the week. There are also solutions that will be posted. It's going to be tempting to try to do the calculations alongside the solutions, but I encourage you to hold off as long as possible for looking at them. And I put links to a couple of podcasts that describe the difference in confidence in learning when watching somebody else do something versus trying it yourself. So you'll have the solutions available, but I encourage you to try the calculations first. To do the calculations, there's one other thing I have to introduce, which is this parameter called gamma. It's called the adiabatic ratio, or the adiabatic parameter. And it's equal to the ratio of the constant pressure heat capacity for a substance divided by the constant volume heat for the substance. So you're going to see gamma in the worksheet, and just know that gamma is Cp divided by Cv. And we'll talk about what we can learn from gamma as a material property in another video. Okay. So the Carnot cycle is 4 steps, like many of the cycles we've tried. If we start here at state 1, and your worksheet does start here at state 1, the first step is isothermal compression, and in your worksheet we're going to specify that we're isothermally compressing to half the initial volume. So here's your isothermal process on the PV diagram. And we're isothermally compressing to where V2 is equal to half of the initial volume. The next step is adiabatic compression. then we'll again compress to half of the previous volume, which means that we have a total compression ratio of 4:1. For people that design engines, compression ratio is considered to be a figure of merit. The next step is again isothermal, this time expansion. So this is where we're extracting work. I'm not specifying what volume it gets to. And then the last step is again adiabatic compression. So it's 2 isothermal steps and 2 adiabatic steps. So this is how we define the Carnot cycle. When I'm solving a full cycle, there's a table I like to use, and your worksheet has that table. So here's what your worksheet looks like. I've written out the conditions that we're doing the cycle under and pre-filled elements that you know, and your job is to go in and fill out the rest of this table. I have a suggestion for how to approach this in the steps below. So that I won't pause this video and I won't come back, but you will just have to go over the solutions, but you'll have access to the solutions on the Canvas website. All right, good luck and happy calculating.